Well, it was still very nice. Mhm. Hey, what are you going to do? All right, this is where we kind of left off. I clunked that up. So we were looking at effectively what goes on. We're the autonomic nervous system. Remember this? This was a very good summary that plays a lot. Oh my goodness, I'm so sorry. Oh, well, you if recording, you would have seen it. So this is this is like fight or flight. If you just look through this and look through this, I mean, it tells you. You can see the ones where it says no effect, no effect, no effect. I mean, those are, like I said, if you remember what it does here, it's fairly easy to remember all those things. I don't think it's nearly as difficult. Okay, and this is, I can't tell you, this was the anecdote, and we're going to go right into endocrine after this. But when it comes to, we underestimate the impact of these things in our lives until it does it. So, the autonomic nervous system is such a complication in diabetics, and we know it's coming to about one third to one half of all diabetics. The hardest thing to do, and this is it, is really aggressive sugar control early. As soon as they're diagnosed, and this was the whole idea of the Joslin Center. Joslin Center out of Massachusetts and Mass General basically constructed a whole means of addressing diabetes to limit complications. And it wasn't just per person. It wasn't just make sure you take your insulin and watch your diet. It was involving the whole family. It was getting them in exercise programs and changing the eating habits of the family so they could do that. And so they all had to kind of work together. And really the framework was an aggressive sugar control, making sure that you addressed any changes in their sugar. Because all of these things happened with this. They were very, very prone to, as we'll talk about, orthostatic hypertension, problems with urine, difficulty this by impairing these mechanisms. They were so prone because the nervous system didn't work. Imagine you and I will turn the shower on, we'll get it hot enough, particularly these days, and you stick, okay. Well, a diabetic could burn themselves if they're not careful because they can't sense that. Sure.
Is that part of the reason why people with diabetes have like tingly feet?
For sure. They do, as we call them, paresthesia. A paresthesia, Paresthesia, is abnormal sense. It's something it's like needles and pins. It's feeling funny. It doesn't imply that there's an absence of sensation, but some diabetics have sensation is completely absent. It's things that you feel that are there that shouldn't ought to be there at that time. And so you have to be so careful with it. Their feet will feel cold, and they'll get a hot water bottle, and the next thing you know, you're dealing with second and even third degree burns, and you're going to end up with amputations. You just, oh, I've seen this movie too many. Okay, so it's under control. The central nervous system, the hypothalamus is the big players in this. There are overrides, and this is the idea. We can. It's typically subconscious in the way it is. It's like when you and I get excited about something. Sometimes we're reacting emotionally. We really don't know it, but those are where it can really impact autonomic function. We all of a sudden our blood pressure is going up, our heart rate's going up. It's like when I was at the funeral. I know my wife felt it because it took her 2 days to sort of come because you're ready for some kind of drama. Fortunately, she and her sister have been at odds about what was going on with her late mother for entirely too long. And I mean, I was afraid there was going to be so it was affecting me the same way. It's like, oh, so my kid got on the phone last night. My son and daughter, when I go, did the funeral go all right? Yeah, my son goes, was there any drama? I said, thankfully not. So all of that's part of it. So you can see this, the brain stem and the reticular formation, that's the one, alert, arousal, probably has the most direct influence. So it's almost like when you and I get up, all of a sudden now those controls are going to, the autonomic controls, it's almost like the switch goes on. We're up now, go to autonomic mode. So the medulla, heart rate, blood vessel diameter, we can't control that. GI, midbrain, you remember the third cranial nerve, pupils and lens, spinal cord, defecation, urination, that's micturition, passing urine. We can override those, as long as we have the capability of doing so. And so there's a lot of different things that are part of it. So the hypothalamus itself probably is the most significant: heart, blood pressure, temperature, water balance, endocrine, and then certain other things, like I said, play a role. When we have rage, fear, that's the limbic system, that emotional center, activating fight or flight. And that does it all. So there's overrides. It's sort of obvious. I'm just sort of verbalizing it to you to understand. There's such a degree of complexity that it's sometimes hard to understand. So the connection of the hypothalamus to the limbic allows cortical influence on the autonomic nervous system. Biofeedback is interesting. I do not know if we're still using it as much for stress or migraines. I saw it used early on. We were seeing that that same summer I was telling you about back in 1976. They were hooking up wounded veterans who were quadriplegics and paraplegics in an effort to try to overcome certain problems that were like headaches and things like. They were hooking them up to. So they were looking at an oscilloscope. It was way before computers. They were in their infancy. So they're hooking up to a cathode ray tube with brain waves, trying to, being able to see if they could exert control to deal with stress and migraines. Because obviously, imagine it's a very difficult, very, very difficult existence with those kinds of things. I had a very, very large spinal cord. So I don't know if they still do it. I don't know enough about it to really comment on it. Would be the best way to describe it. So probably the most common of all these disorders that tremendous number of people have, particularly as they get older: high blood pressure, typically overactive sympathetic vasoconstrictors. The heart works harder. There's much easier to damage, and chronic damage of blood vessels can be real big problems. This is where most of the high blood pressure agents impact the system. It's less about adrenergic blockers. What we're using today more than anything else, because these are the blood pressure medicines I take. Okay, you're going to see one involve something. We're going to look at an endocrine called the renin, angiotensin, aldosterone system, and the other one I've commented on. We use calcium channel blockers. These are calcium channels in smooth muscles. Read that as blood vessels, from allowing extracellular calcium to come in. And if you know someone on high blood pressure, dollars to donuts, they take some type of calcium channel blocker. The one that I think is the most common is called amlodipine, which I take. Used to be called Norvasc. That was its trade name when it was very, very young. It's all the time. This is a very interesting one. Raynaud's. There's something called Raynaud's syndrome and Raynaud's disease. The difference is Raynaud's phenomena and Raynaud's disease. Raynaud's disease, we do not know of a cause per se. We think it's an autonomic disorder. And what's very interesting about it, it starts with normal blood flow to the fingers and toes. Then it gets constricted. Then it opens super wide. So it's painful and exaggerated for its vasoconstriction, and then vasodilation of the fingers and toes. The constriction is the culprit. So what we utilize are typically agents that vasodilate, like those calcium channel blockers, to be able to avoid this. When you see the term Raynaud's phenomena, it's typically associated with an underlying disease that is usually an autoimmune disease. So it's not unusual to see it with people with lupus, to see it with people with rheumatoid arthritis, or other kinds of what we feel are autoimmune phenomena. It's interesting. Now, the autonomic, I'll get to it I'll finish it in a second. Just to get this, the autonomic dysreflexia, so I was talking about quadriplegics, people with spinal cord injuries. It's just that the autonomic it's not reading its signals, and it can cause extraordinarily high blood pressure episodes. And perhaps, as I recollect, maybe that was part of the biofeedback. That's Raynaud's. So what you see, normally you have, and it's typically bilateral and symmetrical, so it's, fingers and toes, if it's usually both hands at the same time, toes both times at the same time. So bilateral and symmetrical. They'll go from being normal color, pale, to being blanched, almost white, and so this is, for those of you, we were talking about it a little bit in MCAT today. When a vessel goes into spasm, no blood flow, it goes from being pink to white. It builds up a pressure head, and so when you release the spasm, there's an over amount of blood flow. And what that does is it congests venous return, so it gets kind of a blue to purple color. It actually becomes a little cyanotic. So we used to call it the patriotic disease, because we go from red to white and then blue. And that's how you kind of remember what was going on. It's a neat way to remember it. All these little things. So it's a very interesting disorder. There's something that's mistaken for it and this is the same thing. I saw this I knew about it beforehand. I saw this at that same Veterans Hospital. We were seeing people with this, and then a guy came up to us with fingers that were white and sometimes very, very dark, almost looked like they were becoming gangrenous. But it was a regular pattern. It wasn't the same on both sides. It was typically on one hand. The same hand was holding a cigarette. Did not know you used to be able to. That's hospitals back then in '76. So I would sit there, we'd be talking with the attending in his office, I'd be having a cigarette. He'd be having a cigarette. Because I think it's changing. And a guy, and it was a condition called TAO, which stood for thromboangitis obliterans. And it was almost as though someone had an allergic response. I don't know if it was to nicotine, but smoking. It didn't happen to everybody, but a very small percentage, but a significant amount of smokers, their blood vessels would go into spasm. We didn't understand the reasons. Asymmetrically, in a regular pattern, fingers and toes, to the point where they'd be holding a cigarette while their fingers were turning gangrenous, because there would be no blood supply. And this guy was demonstrating. And a lot of, and it's, with medical students and interns and residents, it's one of those neat things where you could show them a picture and they might say, oh, that's Raynaud's, but the reality is it's something else. So I'm just mentioning it to you to let you know that funny things happen. And if you're going to go into a field, it really is good to be acquainted with not just what something looks like, what something else might be mistaken for. So very interesting to see. And that's sort of basically the end of autonomic. It gives us time to introduce endocrine. I loaded the endocrine PowerPoints, and I have a handout that goes with it. We've probably indirectly talked about endocrine. I guess the best way to frame it. Nervous system, fast. It's the fast control system, rapid response. Endocrine, slow. Not slow, oh my God, forever slow. It's endocrine, if it's fractions of a second for nervous system, it's seconds, minutes, hours, days for endocrine. It just depends on the system. Slow might be, rather than fractions of a second, just a second or two, or it could be much more prolonged. So effectively, this is much more of a chemical system than anything else. That's the frame. And they work together. So endocrine works by way of chemicals we collectively refer to as hormones. What makes it endocrine, it is a ductless system, meaning it's not a passageway that carries it from point A to point B. It utilizes the bloodstream effectively. So these are hormones that are carried by, many dissolved within the bloodstream, that are produced by certain organs and basically target other organs. Some have a very, very wide range of targets, some very, very limited. Exocrine, the implication is a gland that has a duct, a sweat gland in your skin. We studied in advanced anatomy. Basically, that's a duct that leads to a surface. Another one that you will see when we get to digestive, an example of the pancreas is what we call a double duty because it has both exocrine and endocrine function. The pancreas secretes insulin and glucagon. That's its endocrine function because that goes directly into the bloodstream. Its exocrine function is basically secreting digestive enzymes and fluids and chemicals that pass by way of a very large duct, which you might remember forming something called the common bile duct or the hepatopancreatic duct, a vessel that goes by way of the pancreas and joins with a vessel coming from the liver and enters into the small intestine by way of the duodenum. So you have exocrine and endocrine. Our focus here is exocrine. It's not the only one. Ovaries and testes are also double duty. The exocrine function, eggs and sperm; the endocrine function, testosterone, estrogen, and progesterone. It's not that complex. So the responses are slower but last longer, and we study the organs and we study the hormones. So nervous is rapid versus slow. Faster it has an onset, the faster it goes away. Shorter duration versus longer. Neurotransmitters, hormones, very specific, much more diffuse. So when you talk about human growth hormone, nearly every cell. Insulin, nearly every cell is affected by it. Thyroid hormone, nearly every cell. But if you're going to talk about something called follicle stimulating hormone, it's very specific to ovaries and testes and has them make either eggs or sperm. Basically mature eggs or make more sperm. And here, short distances versus long distances. So all of these things, reproduction, growth, etc., electrolyte imbalance, metabolism, defenses, blah, blah, blah. Exocrine, sweat glands, salivary glands work by ducts coming from your mouth. Remember them? We had the parotids, we had the sublingual, we had the submandibular, all those guys. And they go to a membrane surface. The surface could be external, like the skin, or internal, like the hepatopancreatic duct. The surface, in the case of the hepatopancreatic duct, happens to be this, which technically is a surface, is the lining of your gut, which is the surface, but even though you think it's inside, it's really not. And the endocrine glands, ductless. Very limited system anatomy. Not a whole bunch to it. So you have a limited number of glands, and let me tell you, the glands are tiny. So there are little things that are very, very powerful. So the hypothalamus is both part of the nervous and the endocrine system. You might recall me in anatomy saying it's the neuroendocrine link, which is what it is. It's that area where, by and large, the blood-brain barrier is the weakest, and because of that, chemical levels in the bloodstream are interpreted by sensors, and that information is sent by way of first the hypothalamus, and then to the posterior pituitary, and then to the pituitary, and then all throughout your body. So that is a link using a portion of your brain that can do the sensing, sending a series of chemical signals to that portion of your body that handles chemicals, basically mediating responses body-wide. That's the neuroendocrine link. Double duty, as you can see here. Other tissues and organs that make hormones, fat cells, the thymus. Lots of cells in the walls of the small intestine. You're going to see that when we get to digestive. Stomach, kidneys, heart, etc., etc. Not a whole lot of, does not occupy a whole lot of real estate, so to speak. Does it? Very, very tiny, in the brain. Thyroid might be as big as any of the structures that's on either side of your Adam's apple, the sort of fleshy area. The thymus looks large, but shrinks from the time we're born. It basically becomes flattened and relatively vestigial underneath your breastbone. If you remember, some of you might have dissected. We didn't do the fetal pig, but when you do a fetal pig, it's easy to see the thymus between the heart and the sternum because it's fetal. And then it shrinks. It doesn't mean it stops working. It just shrinks in size and becomes somewhat, the term we would use, we say vestigial. It almost looks like it isn't there, but still making stuff. So hormones travel in the blood or the lymph. We deal with this more in the immune system. Autocrines and paracrines. These are hormone-like substances that work more locally. Autocrine, imagine a chemical that's produced by a cell that influences the cell. You might think this is unusual. The classic cell is in your stomach. It's called an enteroendocrine cell or G cell because the big G stands for gastrin. When you put something in your stomach, stretch receptors trigger this, and it makes basically a product that tells your stomach, get busy, somebody's eating. And it stays busy as long as it keeps getting stretched. So it basically saying we're engaging stomach activities until such time as no more food is entering. Makes sense to me. That's an autocrine. So it's really, classically, that would not be part of the hormone system, or the endocrine system rather. And para means alongside of, chemicals that affect cells different than those secrete them, but by implication locally. They don't necessarily have to or are obligatory to travel by way of the bloodstream. So autocrines and paracrines by definition are local. They're really not part of it. A lot of those paracrines are prostaglandins, chemicals that we talk about a lot. We talked about it with the MCAT folks today with local messengers involving in reproduction. And what was the other thing? We talked about it recently with them. And the other area is the immune system. So, I mean, if you start to talk about, you guys taking immunology, you start talking about interleukins and things like that, those are paracrines. That would be a good example. IL-1, IL-2, IL-17, blah, 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 IL-10, the ones we know about. So there's a lot. Those are important. TNF. You got that tumor necrosis factor, alpha and beta. So that means you guys can even sleep more than you typically do when we do immunology for you guys, or when we do the immune system chapter. You can take the chapter off. You're already getting it. I'm going to watch. You can bring a pillow. I won't say anything. Snooze alert. Just don't snore. Like that. All right, how do we categorize them? By what they're made of. They are either amino acid / peptide based or proteins themselves, and the other ones are steroidal based. And what do they have in common? All the steroidal ones are made from our old friend cholesterol. So all the ones, estrogen, testosterone, progesterone, those are gonadal. And you'll see the adrenal cortex with things like aldosterone and cortisol and a variety of substances we generally refer to as androgens. Those are all based. What's the difference? These are fat soluble. These are water soluble. Wait! I have told you an untruth. There is an amino acid based hormone that is not water soluble. WTF? It's amino acids. They're all water soluble, right? So why the difference? I'm talking about thyroid hormone. So thyroid hormone is made of 2 tyrosines. So you have, just to draw it generically, you have a tyrosine here and a tyrosine here. They're arranged, it's almost like the anti-parallel that we associate with DNA. They're arranged symmetrical. So you have two things that are symmetrical, okay? Effectively, their relationship is much more non-polar than polar. And the only thing we have that's different between them is that one of them has 3 iodines, we call it T3, and the other one has 4 iodines, we call it T4. Thyroid hormone, because of its symmetry with the 2 tyrosine molecules, just not with the iodine not making a big deal whether it's 3 or 4, by definition, kind of we group it with the fat soluble, or quote unquote lipid or fat soluble hormones. What does that mean? All the other amino acid based ones dissolve in the bloodstream. Thyroid hormone and the steroidal hormones require carrier molecules. Okay, and they work differently. The amino acid based ones, with the exception of thyroid hormone, they utilize G protein receptor passageways with second messengers like cyclic AMP and calcium. Whereas the steroidal ones, they contact receptors either in the cytoplasm or even in the nucleus and nucleoplasm itself, and they don't impact through second messenger systems. They utilize, directly affect transcription, translation. Once they contact the receptors in the cytoplasm, or in the nucleoplasm, in the cytoplasm, let's take that for example, that receptor complex crosses into the nucleus by way of the nuclear membrane and directly impacts transcription and translation. It expresses itself like most things do by making protein. Got it? Hey, we are almost done. These are not. Most of us classify the eicosanoids as paracrine type substances. Those are, when I talk about prostaglandins, so named because they were originally, identified in prostatic fluid. So that's where it's a prostate gland. You remember what those are? Those are those long chain essential fatty acids. Ringing a bell? They've got the couple of sites of unsaturation and they sort of fold and create a bond, right? You didn't get to that yet. This thing?
We did go.
Yeah. So you get this long chain, and basically it sort of forms where the two bonds will form this way. It sort of, here's the acid, long chain fatty acid. This is arachidonic acid. It's an essential fatty acid. You have to get that essential, again, everybody knows by diet. Where do we find arachidonic acid? I had it for breakfast. Peanut butter. Thank you. I'm a peanut butter addict. Peanut Butter Anonymous. Sorry.
A shirt that looks like peanut butter.
Thank you. Oh, wait do you see the one my daughter got for my gift for the wedding, for the rehearsal dinner? She gave me one. She knows my affection for the movie The Godfather and all the stuff about it. It's called The Bridefather. I was going to do the whole thing. I was going to wear the Don Corleone, men's tuxedo, almost. What have I done to treat you so disrespectful? I love that. If you have some time and you get Paramount Plus, watch a 10-part series called The Offer. It is so good. It's beyond good. They do a great. It's not 100% true. But the guy is still alive, who, the Miles Teller role. He's in his early 90s. So, I mean, he was the producer for that. It's just fascinating. Just in case you run a little historical information is important. So here, this will just summarize this. So the hormones circulate systemically, but only target, so they're going through your bloodstream, but so if it's, let's say, follicle stimulating hormone from your pituitary, it's not going to impact any other cells other than those with receptors, and those are going to be associated with ovaries and testes. So they have to, it's receptor based, and they will in some way, shape, or form alter the activity. And there's a variety of ways. That's the beauty of G protein receptors, because whether it's like insulin, membrane permeability, reactivity, opening and closing ion channels, synthesis of a variety of other proteins. Insulin does all this. Activating or deactivating enzymes, secretions, mitosis. I mean, and again, insulin and human growth hormone are very good examples of many of those actions. They're all over the place. So the water-soluble ones, except the thyroid, plasma membranes, G protein receptor systems, as we talked about before, can't go in. The lipid-soluble ones, intracellular, typically cytoplasm, can be nucleoplasm, and enter the cell. Second messenger, cyclic AMP, that PIP2 calcium, that's whatever's PIP stand for, that's Dr. Hilwig material. Anybody remember? I always forget the acronym. You can look it up. I mean, I just say calcium and be done with it. So I'm not going to do this and rebuild the wheel, but you know how this works. The first messenger, external, can't enter the cell, activates the G protein sequence. The big player is that adenylate cyclase. The adenylate cyclase, that's the one that is able to convert the ATP, utilize the energy from those high energy phosphates to generate the second messenger of cyclic AMP. And then that typically has that sort of cascading effect, activating kinases. As you will see, the one we best understand is tyrosine kinase. That's the one that's activated by insulin. So that's understanding means it's been studied. That's all. We don't go into the intricacy of it. So, I mean, and then they phosphorylate proteins and, they activate, inactivate, blah, 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 blah. And again, the typical one, which I always think these are kind of neat. But, I mean, you can buzz through it the same way I can do that. And here you are, basically the cyclic AMP basically being the catalyst to activate whatever protein kinases we're talking about, and then activate this whole cascade of effects. So, and these are the different ones. Not doing that. That is Dr. Hilwig's material. You want to step on our toes, so to speak. So we have enough names in our lives. Okay, another one. So the calcium ion acts as another second messenger. Calcium, remember look what it bonds to, calmodulin. Remember in smooth muscle, when calcium bonded to calmodulin, it caused a shape change. Same thing that happens here. And remember, in smooth muscle, it activated that myosin kinase. Telling you that for a reason, it's on the test. See? You have to thank me, part of the service. And it activates the enzyme system. And so, and it's not the only ones. Insulin, tyrosine kinase, and that autophosphorylates upon insulin binding, and blah, 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 blah. And there's all sorts of stuff that goes on. I mean, trying to think of it. Endocrinology is a field unto itself. Diabetology is a field unto itself. In medicine, you have courses in this alone, and a lot of times, even in diabetology, that's a board certification as endocrinology of its own. I mean, it's remarkably complex. We would go to conferences that had one topic, diabetes. Spend a weekend learning about this and that for years, trying to figure out what caused diabetic peripheral neuropathy, because they had come out with medicines trying to combat that. None of them have They were more harm than good. Lipid soluble thyroid, intracellular targets, complex, enter the nucleus, binds directly to DNA, and initiates transcription and translation, as you can see. And it's controls, and they go through these illustrations. Typically, they're pointing out the complex, the receptor and the hormone complex being here, them being able to enter by way of some nuclear pore passageway and impact. And we'll skip that. By and large, this is all limited exception. Very much negative feedback 101. Well, I'm not going to do it today. I'll talk about an ARC very soon. Hold on. The boss, question. Okay. Sorry. If I don't answer these, you'll have another lecture tomorrow. So, by and large, it's all negative feedback. We will look at the ARC, ARC, and effectively what we're going to be looking at, I commented on it a little bit before, the blood-brain barrier being weakest in the hypothalamus. And then if we start there at the hypothalamus, effectively that's the sensor. There's a variety of ways we can feed back. So that's sensing, that's going to send the signal effectively to the posterior pituitary. The two posterior pituitary related structures are part of, so this is brain, this is nervous system also, but by definition we call it the neuro, for nervous system, hypophysis. HYPOPHYSIS indicates that the posterior pituitary is also called the hypophysis. That will send signals by a variety of chemicals to the anterior pituitary. That's the glandular, so we call that the adeno, which means gland, hypophysis. And that will send the hormones out to their target. And a lot of times we can negatively feedback by what the targets, by chemicals the targets produce. We can feedback by way of some of these chemicals as well. So, and by and large, it's that the beauty of negative feedback, find control. We're sending out something called luteinizing hormone because we're lowering levels, we're detecting lower levels of estrogen and progesterone or testosterone. As the levels start to rise, the signal gets less and less until eventually it's not needed. It's just that dynamic balance, and it's several changes constantly. Nearly all of the endocrine system is like that. And so very, very narrow, desirable range they're kept in. And whether it's endocrine glands themselves stimulated, we can modify it by the nervous system. How does that work? Fight or flight. And there's a lot of that goes on. Let's leave it there and we'll cover all these stimuli with a few minutes left to spare. Send you folks on your merry way for a good weekend.